Hello. So in this video, I'm going to show you how to implement the Horvitz-Thompson estimator that we learned from the textbook section 3.3.2 on Stata. So we discussed this estimator theoretically in the textbook, but I feel like I had to show how to implement that. So this is not a homework. I'm just showing you the actual implementation, which is pretty easy. So that is just in case if you happen to use this estimator in the future, then maybe it will be helpful. So let me review what we have done. So first, we would like to estimate the average treatment effect. It is unweighted, naturally weighted expectation of everyone. And that what we need is the conditional independence assumption, assuming that the treatment is independent of all the potential outcomes conditional on other variables. And then under the conditional independence assumption, in the textbook equation 3.3.11, you will be able to find this equality. So the left-hand side is what we wanted. This is what we want to estimate. And the right-hand side is a function of like an expectation of y, d, which are observed, and p, which is the propensity score, and you can estimate that. So on the right-hand side, everything is estimable, but left-hand side, we don't observe either one of them, so we cannot directly calculate the left-hand side, but you can calculate the right-hand side. So we call the right-hand side term as the Horvitz-Thompson estimator. We are going to calculate this average. It's some kind of expectation, so it's in the end it will be an average involving estimation of propensity score as a preliminary estimator. So the data we are going to use in this example is based on the tables 3.3.2, 3.3.3 in the textbook. So that is the CPS data, current population survey data, which is a huge data set, and we are going to consider the effect of a job training program on future earnings, right? Whether job training program improves earnings or not, by comparing those who participate and those who don't participate, right? So our variables are defined this way. The treatment is participation in a job training program in 76 and 77, right? And what you observe is earnings in 78, which is like future earnings, like 1 year after, 1 or 2 years after participation of the job training program. So basically these two, we are looking at the relationship, causal relationship between these two variables. But additionally, we would like to include some control variables that affect the participation decision. So participation in a job training program is not random, because you have like the worker has to apply for it and attend it, right? To finish it, it's not random. You cannot force them to come and attend. So therefore, we try to include control variables that affect the participation decision, which include, in this data set, I use age and age squared. The reason why I'm including age squared is because, so usually age, like when you include linear term, it's just keep increasing or keep decreasing. Linear function is only one direction, but age may have this kind of effect. Like, so when you are in 20s, like the older you got mature, so you are more likely to participate. But at some point, when you get old enough, you feel like you don't need to attend the participation program, so then it goes down, right? You understand? So like this is possible. I'm not saying this is the truth, but because of this kind of possible scenario, we try to include square terms. So because the quadratic function looks like this or like this, so to include some kind of curvature, potential change of direction like that, we are including square term. But it is not a big problem at all on computer. So you will see including a square term is not a problem. And years of schooling, education, which is an important variable, and racial dummies for Hispanic and Black. And we, even if we include schooling variable, we additionally include high school dropout dummy. So if one did not finish the high school, then we indicate that person because they are particularly vulnerable and particularly maybe most desperate and most beneficial guys from the job training programs. So we expect there should be something special for those who drop out of high school. So we include those dummies. Even if it does not matter, still not a problem. Including additional variable does not cause any problem. So marital status. We include this because if you are married, then there will be additional pressure to do something to find a job. So like we expect marital status will affect job training programs. And also, what is interesting, what is available is the earnings in the previous years. So before getting unemployed, in the earlier years, how much the worker may earn. So that will affect the decision on job training program. If a person has enough financial buffer, then he's less likely to participate, something like that. So anyhow, these variables are the same set of variables used in the table that I mentioned in the previous page. And by the way, those data can be downloaded from the author's webpage. So the Joshua Angrist's webpage has the data on web. So if you are interested, you can download it, right? So then let me review what we need to do to implement the Horvitz and Thompson estimator. It's simple two-step. First, we need the propensity score. How can we estimate that? We are going to use the Probin model. So we learned what is a Probin model. We are going to use this, and we will use Probin model to estimate the propensity score, and then using the propensity score here, propensity score goes here, and then calculate. It's simple. Something divided by something, multiplication divided by something minus multiplication divided by something, and then take average. So it's pretty simple process. Let me show you. So again, this is Stata. Like as before, I'm going to change my directory to C drive Horvitz and Thompson estimator, and I will open the data set. I'm going to upload the data set with this and with the results, the data set and the code on Blackboard, so you can find it there. So by the way, this is the data set. Look at this. So treat is the treatment, age is age, ed is education, Black, Hispanic, marital status, non-degree, no high school degree, and real earnings in 1974. So I mean it's inflation adjusted real earnings 75, real earnings in 78, and age squared. So all the data are already cleaned. So now it is pretty easy to implement. Like I'm going to do the same process twice. First, I will use this command window, right? That's to have an instantaneous result. I explain the command, and then I would like to show you the result instantaneously. that is done here. And then in the second step, second iteration, I'm going to write the same thing on two-file editor. So this is the right way. This is recommended way using the two-file editor. But because I'm teaching, I'm showing you what to do and what you get. So I use this command. But if I did not teach you, I would not use this at all, right? So please understand, I'm using this just because of just for educational purpose, right? Anyhow, so what I'm going to do first is I will summarize. I will see what's going on in the variables. So let's see. There are 16,000 observations, and 16,000 observations. Already the data are cleaned. There is no missing variables, right? Well defined. And think about this. The treatment participation in a job training program has a mean of 0.01. Like this means only 1% of people, 1% of observations participated in a job training program, right? And average education was 12 years, which is high school. Average age was 33 years old. And black, there are 8.2% black, 7.1% Hispanic, and 70% were married, and 30% did not complete high school, right? And average earning, like real earnings in 74, 75, and 78, right? It looks like there is a higher earnings in 78, and squared, it's age squared. So average age was 33, but when you square it and take average, then it becomes more than 1,000, which is just average of squared age. So what I'm going to do first is I will use Probit model. I will use Probit model to estimate the probability of treatment. Remember, Probit model uses treatment on all the other variables, but I excluded the outcome, right? Remember, go back to the slide. Propensity score is the probability of treatment on control variables. So outcome variable does not affect the propensity score. So I do not include this outcome variable, but everything else. Then it will estimate the Probit model. Takes a second, but so this is the result. But we are not interested in the coefficients itself. So for example, the higher the older, the more likely to participate, and so it is interesting. The squared age is significant. P-value is 0, so it's pretty significant and negative. So that means the functional form is like negative, like the quadratic function with negative coefficient, right? So, but anyhow, it's not a big problem to us, not of interest to us. But what we want is we would like to define another variable here that defines the propensity score. To do that, the command you can use is you may use post-estimation prediction, right? Probability, or so this is what you can use, or I would just simply use predict. So you are going to predict the expected value of treatment and define this as propensity score, right? So the command is pretty simple. Predict this Probit outcome and define the result as propensity score. So let's simplify this. P-score. Then we have another variable. This is exactly what we wanted. We have p-score variable. Let's look at that. Let's have a look at. So this is the new variable calculated using the probit model, right? So it's probability. It's between 0 and 1. So you can interpret this is the probability of receiving like participating in a job training program given these observations. Okay. Anyhow, so we get propensity score. Then the next step, we just finished the step number 1. Was just simple 2 commands, probit and predict. Then that's pretty simple. And now we have to do the second step, which is just a kind of average. What I'm going to do first is I'm going to calculate this guy in the parentheses as another new variable. So I will generate a new variable. Let's say I will define that as Horvitz-Thompson HT, which is defined as so treatment times RE78 divided by p-score. So I just calculated the first term. So y times d divided by propensity score. So y times d divided by p-score, that is the first term minus, now 1 minus treatment times outcome divided by 1 minus divide by 1 minus p-score. This will generate, like I will hit enter. So we have another variable that corresponds to this part. So what we need to do is we just need to calculate the average of this variable, right? Think about this. Y times d divided by p minus y times 1 minus d divided by 1 minus p. That's exactly what I do. Y times d over p, 1 minus d times y over 1 minus p. Okay? Then finally, what you need to do is mean HT. This is the result, right? The answer is if you participate in a job training program, the expected outcome is minus $6,700 in your income, which is pretty strange, very strange outcome. I expect this is because the endogeneity is still remaining, right? So it is not randomized. So the conditional independence assumption is still questionable. So that's why the result is pretty weird, right? So anyhow, we are just assuming. So if the assumption was correct, this is the correct causal estimator. But if the estimator is weird, then you have to think about whether the assumption is correct or not. I guess it's dubious. And anyhow, so it is purely about implementation, and even the textbook does not show that result. Maybe because the result is too weird. And anyhow, then another thing I'd like to show you is propensity score screened regression. That is what is used. That is the result shown in the textbook in table 3.3.3. So they show the regression. They use regression in the end, but they wanted to choose their sample using p-score. That is what you are going to do. And there are also 2 steps. First, estimate the propensity score, which we already did. And we are going to delete, we'll choose, restrict the samples so that by deleting observations with p-score less than 10% or greater than 90%. So we will use people in the middle and then use regression in the end. Let's see. So we already have p-score. Now, what we are going to do is we will drop if p-score is less than 1, less than 0.1, right? So drop if p-score is less than 0.1 and drop if p-score is greater than 0.9. Right? There is no one actually who has p-score greater than 0.9. And then now what we do is, that is the end of the first step. We already did the first step. We trimmed our sample using the propensity score estimate. And then we will regress the outcome on treatment and all the other control variables. Of course, you do not include propensity score or the new variable, the new generated variable, because they are not control variables, technically defined variables. So just do the regression. By the way, the authors recommend to use robust option because this is it changes how you calculate the standard error. So standard error is theoretically more advanced and more accurate. So anyhow, so you are going to get this result, and what is interesting is, like, now you can interpret this as the coefficient of the treatment as the causal estimator, right? So causal estimate is 1300 plus 1300. Compare that to the Horvitz-Thompson estimator. It's minus 6700. But if you use a little different method, it becomes 1300 plus 1300. So you know what? It is really weird. I agree, it's really weird. But what would I choose? I would take this as my estimator, right? I would not believe this. First, even if we learn statistics and like assumption theory, but I recommend you rely more on your intuition, right? That is actually sometimes much better than what theory predicts. And another thing here is, so in the end, we are going to use only 500 observations, right? So that means like this Horvitz and Thompson estimator uses 15,000 observations, like nearly like more than 90% of observations are deleted in this process. But this makes more sense because think about this. 15,000 people, most of them are just like normal. Like, I mean, they are not desperate workers. They even do not consider participating in a job training program. If they have just stable job, then you don't worry about job training program and finding another job, right? So that is 15,000. 15,000 people have less than 10% probability participating in this job training program. And that means then that causes the denominator is less than 10%, less than 0.1, which means it is numerically a problem. Denominator is small, that means the numerator becomes huge, right? So the fraction becomes huge. So statistically, this causes inaccurate result. So anyhow, so to explain why the results are so weird, there are many other reasons. But also another lesson you have to learn here is, depending on which method you are using, the results could be totally different. Then if you are evil, you may use it this way. You want to just justify your conclusion, justify your opinion. You may choose one of the methods. If you had enough methods under your usage, if you knew more methods, then you could make up the results as you want. In other words, or if you'd like to refute an existing result, you could try another method. Then the result could be totally different, so you can fight back those the opposing opinions. So this is not a desirable use of statistics, but that's reality. That's the truth. You have to you'd like to include more weapons, more methods in your arsenal, so that you can choose the weapon that is best for you depending on the situation. So this is another lesson, even if it is not beautiful, but the dirty reality is the truth. That's the reality. Okay, as I promised, I'm going to do the same thing on the two file editor. So open two file editor by clicking this button. Then you are going to get a new one. So then I will start with some basic titles like implementation of Horvitz-Thompson estimator and p-score screened regression. You can just buy Park. You can put names and a lot of things, just annotation. AECO 480, 580, Statistical, Causal, Inference, SUNY Albany. You can just write whatever you want, just as long as you use these two parentheses. Start with this and write anything, blah blah blah, and close with this. Then they are not recognized as a command, so not a problem. So then let's go back what we have done. First, I have to include change directory and loading the data. So first I will change my directory. I just copy like this. So of course the folder may be different on your computer, but it's your choice. And now when you change the folder, you don't need to write all the folder path, but just like this. And one thing that I usually use is I put replace option. So when I use replace option, this means use this data set and replace the data in the memory. So when you use this, for example, so far we have made 2 additional variables. That's new variables, and by the way, we did not save these 2 new variables in our memory. So if you use replace option, you may lose these 2 new variables. That is possible, but it will simply just replace that. Otherwise, if you do not use this option, your code will stop here because there is already an existing data in the memory. So it's when you use the replace option, you should be careful to save the existing data. Otherwise, it should be fine. And then so this is loading data, just in case if you it's this kind of annotation will help you understand what you did here. And estimate the propensity score by the probing model. So I can use probing model, treat age, add black, Hispanic, married, no degree, So so I'm just peeking at here and copying this to here. So probit model, simple probit model. So just use probit model with this as the dependent variable and all the other as the independent variable. And then right below the probit model, we have to predict the outcome, predict, and define that as p-score. That is propensity score estimated, right? So that's just 2 lines, and we generate Horvitz-Thompson estimator by generate ht equals, let me just copy it, generate and then mean ht. This is the Horvitz-Thompson estimator. Okay, so when you collect the commands, it's pretty simple. There are only like 2 lines for each step. And what is better is like using the annotation, you can explain what you are doing, and for your future self, like you may forget what you have done, and then opening this code will be enough to understand what is going on and why you use this command like that. And the next step is I will use p-score screened regression estimator. So I will drop if p-score is less than 0.1, drop if p-score is greater than 0.9, right? So, and then regress. Let me just copy it. Okay, copy, paste. Okay, this will be it. So, as I said, because I wanted to show you the result instantaneously, so I used command here. But if it was not a teaching, then I would directly write like this, right? So this is what I wanted to show you. Let me save it. Horvitz and Thompson. Actually, already I have it. Estimator, right? So this is what I do. Let me try what happens. First, let me try with the replacement option. Replace option and run. So then, as you can see, you get a data. Data in memory would be lost. So, there is a data. So, like new data, unsaved data. So, another data is not loaded, but ignore that. We are going to do the same thing. If you include typo here, okay, so I just found a typo, variable non-degree not found. So not a problem, easy fix. I fixed it, and let's try it again. Okay, this is, you will get the same output as before. So this is how we implement Horvitz and Thompson estimator, and more importantly, how we use Stata, how we code on Stata. Okay, good luck. Bye.